This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. And in this lecture, we're discussing Learning Objective 4.3.1, in which we're going to talk about rigid body plane motion velocity. Now, rigid body plane motion velocity is covered in chapter 15, of your textbook. And the basic idea here is that we want to be able to look at any body in 2D and keep track of all the points on the body, what their position, velocity, and acceleration are, whether or not it's both translating, rotating, or doing both at the same time. And so what we do to do that is we combine superposition. So the superposition of translation and rotation will let us describe all 2D motion. So if we look at this figure here, we can see that to get the general plane motion, this is showing position, we have the initial position and then it rolls forward. Well, you can arrive at the same location for A2 and B2 by thinking about A1, right? And it just translates. We could just translate B1, and then you can rotate B1 around A1, right? So the idea is that if we know the kinematic properties for one location, we can then make that the center of the we can make everything translate, and then we can make that the center of the rotation and add those two components together. So if we wanted to expand on this, make the screen a little bigger. For example, I hope you enjoyed a tomahawk toss. If we wanted to keep track of where the tomahawk was going, what we could do is we could say, well, I'm going to keep track of the center of gravity. That's probably close to about here for the center of gravity. Or I could say, I know what it's doing when I let go with my hand, right? So right here, what the velocity would be through that motion. And I want to know what the head is doing. And so let's just for the sake of example, do that, okay? So here's my translation portion where I'm going to draw my velocity kinematic diagram. So I'm going to have my tomahawk look something like that. And this would be point A down here, the handle, and point B up here at the tomahawk head. Now, the idea was to say that we know what velocity is happening at A. And so for the translation portion, we're just going to say, look, here's our velocity at A. Now, remember that when we talked about translation, we said that if we knew the translation of one point, we would know the translation of all points. So if we're just thinking about translation, what we're going to do, if we know the velocity at point A, we also know the velocity at point B. And it's going to be the same as that velocity at point A. So that's the translation component. And if we think about our kinematic relationship equations, basically what we're saying is that the velocity at A is equal to the velocity at B. We know this from our translation discussion that we've already had. Now, if we think about it as just rotating, we would draw a kinematic property diagram also with points A and B. And we would keep in mind that in this case, what we're going to say is we knew the velocity of A over here. So now we want to think about the velocity of B. So if here we were looking at the tomahawk just translating, here we're going to look at it just rotating around point A. And so what we would do is we would say, okay, it's probably rotating. And I'm going to go ahead and just draw it as rotating in the positive direction. So that may not exactly match our acceleration. So there's our omega. And that means that my omega cross R, so this is going to be R, B with respect to A. And then we'll have that velocity at 90 degrees here. So this is going to be the velocity of point B with respect to A. Now, I hope this puts you in mind of that relative motion. What we've got is omega, positive direction. So omega cross R gives me the velocity. And so if we were looking at point B from A, this rotation is what we would experience. And so now we have this rotation component. Now, we said that we could use superposition. So the idea is that if here we can say that the velocity of point B with respect to A is going to be equal to omega AB cross RB with respect to A, which is what this diagram shows. Okay. The other thing we'll note is that your textbook does an excellent job of illustrating it for you, but omega is actually a free vector. Angular velocity is a free vector, which I hope you remember from statics. Moment was a free vector. It didn't matter where we applied an applied moment, we would get the same external constraints. Well, omega is the same way. We can draw this omega anywhere we want. And in this case, we've chosen to draw it around point A. So omega is also in the k direction when we're working in 2D. So we have translation, we have rotation. Now we want to use superposition and add the two together to get our general case. So our general case is going to be the tomahawk in its total motion. And what we're going to do is we're just going to look at point A and add the two components together. So I'm going to have the velocity at A and omega A B. And then I'm over here, I'm going to have the velocity at A plus the velocity of B with respect to A. So if I do a head to tail, not quite, it's got to go at 90. So something like this. And so then that means that this here is my velocity at point B. And so if I wanted to write out that equation, the velocity at point B is equal to the velocity at A plus the velocity of B with respect to A. Hey, that's our relative motion equation. Y'all remember that? Velocity at B equal velocity at A plus B with respect to A. But now A is our translation component, like so. And B with respect to A is our rotational component. So our velocity at point B is equal to the velocity at point A from the translation diagram plus omega AB cross R B with respect to A. So we can just do this relative motion where we add the translation and the rotation components together, and that'll give us the overall motion. So in this case, what we're looking at is the translation, the rotation, and so together it's doing something like that. So I hope you can kind of see how that works. So it's moving like that as it moves. And so that's the idea that we can use. So we're going to use this in acceleration as well. That's in 2 lectures. But the idea is that we can map out our kinematic property diagrams for translation and rotation, add up the points at A, the points at B, and get our general motion. We can use our relative motion equation that combines both our translation component and our rotation equations. And now we can map any 2 points relative to one another. So what we're going to do in class is we'll look at a problem where we know the motion of the axle, and we'll look at a rolling wheel, and you'll have lots of homework where you can practice this. The one other piece that we need to keep in mind is relative motion, or I should say dependent motion. And so before we do our homework problem there, or our in-class example that we'll do together in class, what I want us to do is to talk briefly about cogs and wheels and the dependent motion that occurs for cogs and wheels. So if I have 2 non-slip surfaces, so dependent motion, just like pulleys, except this is a lot less complicated. Dependent motion, non-slip, cogs, gears, wheels. The thing that we have to keep in mind is that they're going to have common, so here's my 2 gears, they're going to have common tangential kinematic properties at the contact. And so what that means is that here we have this contact point. If these 2 gears were rotating, something like this, that at that point, that velocity is going to be the same, because remember, all of the velocity points in the tangential direction. And so we can think about moving from a non-moving center to the velocity, and that'll give us one equation, or from the center to the velocity, that would give us another equation, but they're going to have the same velocity where they touch, common tangential kinematic properties. All right, I look forward to seeing you in class. Rigid body, plane, motion.